And welcome to our new topic. Today we discuss about the Laplace transform. As you know, it is one kind of special function, and that Laplace transform denoted by capital L, and its value is given by one definite integral like beta and gamma function. So Laplace transform is given by 0 to infinity e to the power minus st ft dt. Our parameter when we cannot take the Laplace is t, but when we took Laplace transform of that parameter, it convert into s. So here we can change the parameter. That s new parameter is either real or complex. It's both kind of parameter. So Laplace transform of any function is given by this integral 0 to infinity. And what are the condition for any function? Can we make Laplace transform or not? So number one, it is piecewise continuous. Piecewise continuous means a function ft is called piecewise continuous in the given interval if ft is continuous in finite number of subinterval which obtained by subdividing the given interval. Means if we divide given interval, then it is also in between that interval it is continuous. So this is called piecewise. In each piece it is continuous. Piecewise continuous. Second is ft is a function of exponential order, because we have to expand it with the help of e to the power minus st. So that function is of exponential order. So this is the necessary and sufficient condition. If you have any function, then we can expand in terms of Laplace. So now we discuss some standard form of Laplace transform, or we can say that how we expand any function in the Laplace. So I give you some standard formula, then we go further properties of Laplace transform, and then how we solve the given function with the help of Laplace. So first is the standard Laplace transform ft is equal to e to the power at. If your function is e to the power at, same what is your formula of Laplace transform? 0 to infinity e to the power minus st ft dt. What is your ft? Ft is another exponential function. You replace here. So ft is e to the power at dt. So now you integrate 0 to infinity e to the power minus t taking outside s minus a t dt. Clear? Integrate it and apply the limit. You will get this Laplace transform. We can say fs is equal to 1 upon s plus a. Clear? Here always it s minus a, s minus a, 1 upon s minus a. Here always s is greater than a is the condition for Laplace transform. Otherwise it goes negative. So s is always greater than a. Next, if e to the power minus at, then Laplace transform of that function is, if f is e to the power minus at, then Laplace transform of e to the power minus at is given by 1 upon s plus a. You just simply integrate and substitute the limit, you will get this solution. Next, if our function is second sine hyperbolic of at. Clear? So what are the sine functions? Sine is the relation of exponential and trigonometrical function. Sine hyperbolic at is in my video of hyperbolic function. You can see sine hyperbolic at is e to the power at minus e to the power minus at by 2, and cos hyperbolic at is e to the power at plus e to the power minus at by 2. So we replace here our function is e to the power minus at sine hyperbolic at dt. What is Laplace of ft? E to the power minus st ft dt. Now hyperbolic again replace with exponential function e to the power minus st e to the power at e to the power minus at divide by 2 dt. Now you combine one integral e to the power minus st plus e to the power at, other one is e to the power at e to the power minus at. You have to take the Laplace, then you will get when we apply the limit 1 by 2 is coming outside, 1 upon s minus a minus 1 upon s plus a. So what is this when you take the LCM? This is a upon s square minus a square. So what is Laplace of sine hyperbolic? I give you Laplace of sine hyperbolic at is a upon s square minus a square. Similarly, you can, if you find Laplace of cos hyperbolic at, cos hyperbolic at is given by s upon s square minus a square. You definitely, if you want, you can prove it. Substitute value of cos hyperbolic at in Laplace transform formula. Cos hyperbolic at is e to the power at plus e to the power minus at by 2. Clear? So next is the Laplace transform of sine and cosine function. So if we substitute Laplace equal to sine at, then we have to find out what is the Laplace of sine at is 0 to infinity e to the power minus st. Our ft is sine at dt. Clear? Now here we use the one formula, e to the power ax sine bx. Integration of this is e to the power ax divided by a square plus b square a sine bx minus b cos of bx. This you already learned in your integration. This is the integration of e to the power ax sine bx is e to the power ax a square plus b square a sine bx minus b cos bx. Now you compare what is your a is minus s and b is minus of b is a. So what our integral becomes? E to the power minus st upon s square plus a square. Next a is minus of s sine at minus b is a cos of at, and limit going from 0 to infinity. Now you integrate this integral with the help of this, and now you apply the limits. When you apply the limits, this s square plus a square coming outside, apply the limit at t, e to the power infinity goes 0, e to the power 0 gives 1. So first upper limit gives 0, lower limit, with lower limit this sine term, sine of 0 is always 0. So only this term gives the cos 0 is 1. So this is minus of minus plus, only a is there, a upon s square plus a square. So what is sine at? Sine at is Laplace transform of sine at is a upon s square plus a square. Similarly, if you want to find out Laplace transform of cos at, then definitely you can able to find out Laplace transform of cos at is s upon s square plus a square. Hyperbolic function, sine hyperbolic is a upon s square minus a square. In cos hyperbolic, s upon s square minus a square, but in simple trigonometrical, denominator is s square plus a square. Now we further go for one more very important part of Laplace transform, t to the power n. If we want to find out Laplace transform of t to the power n. So if our function, so what is our 0 to infinity? Fs is e to the power minus st t to the power n dt. Clear? Now for this integral t to the power n, we have to substitute st is equal to new parameter. Let st is equal to, if we can consider st equal to u, then s of dt is equal to du. Clear? If st is equal to u, then 2 by s. U by s. Now you simplify it. I rewrite here. E to the power minus of u, u to the power n, s to the power n plus 1 du. Now you can see e to the power minus t, t to the power n dt is what? Yes, this is the gamma function, gamma of n. So we replace this with 0 to infinity. This is 1 by s to the power n plus 1, and this integral e to the power minus u to the power n du is gamma of, but we have that is gamma of n minus, there is gamma of n, means this is gamma of n plus 1. So we replace here gamma of n plus 1. Gamma of n plus 1 is factorial n. So either you can say n gamma n upon s to the power n plus 1, or you can say factorial n upon s to the power n plus 1, where n is always greater than 0. So this is Laplace transform. I can say Laplace transform of t to the power n. With this help, we can find out Laplace transform of t square, t cube, t4. If I say Laplace transform of t cube, so at the place of n, our value is 3. So this is factorial 3 upon s to the power 3 plus 1, 4. So Laplace transform of this is factorial 3 upon s to the power 4. Factorial 3 is 1 into 2 into 3, means 6 upon s to the power 4 is the Laplace transform of t cube. Similarly, we can find out the different types of Laplace transform. Now we go some properties of Laplace transform with the help of one function multiply with the other function, and so many properties are there. With the help of, we can use those property to find out the Laplace transform. If you remember all those properties, you can easily get the Laplace transform. So now we go for the properties of Laplace transform. Now whatever you learn, you remember, you make a table always for Laplace transform. Number 1, Laplace transform of t to the power n, you write the formula. Then second, Laplace transform of sin at. Third is Laplace transform of cos at. Fourth is Laplace transform of sin hyperbolic at. Fifth is Laplace transform of cos hyperbolic at. And first one, or we can say sixth one, Laplace transform of e to the power at. Clear? So if I say Laplace transform of constant, Laplace transform of 1, Laplace transform of 1 is t to the power 0. T to the power 0 is 1. So we can find out with this t to the power, that is factorial n upon s to the power n minus 1. If n is 0, factorial 0 is 1 by s. So Laplace transform of 1 is 1 by s. You should always remember Laplace transform of constant 1. If here is 2, 3, 4, 2 coming outside, taking 1. If 4 into 1, 4 times Laplace transform of 1 is 1 by s. So Laplace transform of 4 is 4 by s. This all are, you can write, this is a upon s square plus a square. This is s upon s square plus a square. This is a upon s square minus a square. This is s upon s square plus minus a square, and this is 1 upon s minus of a. E to the power minus at is s plus a. So these are the basic Laplace transform formula. You have to remember this, or otherwise you can make a chart, put one side, because always you need these formula when you solve the Laplace transform. Now next we go some properties of Laplace transform. Properties. First one is very easy, linearity property. Linearity means if any constant multiply with this plus other constant multiply with other Laplace transform, then this gives constant come outside, you will take just Laplace transform of that given function. Your answer will, this property is called linearity property. That's why I told you, if we want Laplace transform of 4t, so this is 4 times Laplace transform of t only. So 4 times Laplace transform of t is t to the power n is 1. So factorial 1 upon s to the power 1 plus 1, 2. So Laplace transform of 4t is 4 by s square. Clear? Laplace transform is very easy if you go by formula and you remember all the properties. Next one is the first shifting property. Second property we state. First shifting property. What? This property states that if Laplace transform of ft, we can say this is f of s, then Laplace transform of e to the power at ft means any exponential function is multiplied with our Laplace, then our answer is f of s minus a. Means what? If we have Laplace transform of, we have for example Laplace transform of e to the power 3t sine 2t. Clear? So this is with first shifting, e to the power at is multiplied with Laplace transform. So what we have to just find out Laplace transform of sine 2t. Laplace transform of sine at is a by s square plus a is 2. So 2 by s square plus 4. This is Laplace transform. Now this is our fs. Next, using first shifting property, our fs is f of s minus of a. A is our 3t. So a is our 3. So at the place of s, we have to replace s minus 3. So Laplace transform is 2 by s minus 3 whole square plus 4. It means Laplace transform of e to the power minus 3t, e to the power 3t sine 2t is 2 by s minus 3 whole square plus 4. That is first shifting property. If any given function multiply with e to the power at, then our first you have to find out the Laplace transform of that individual function, then this s replace with this s minus of a. That is first shifting property. Next we talk about the property of second shifting. Continuation of this. Third property is second shifting property. Second shifting property is same. If Laplace transform of ft is equal to f of s, then we can say a new function gt is defined 0 and f of t minus a when t is less than a, when t is greater than a. If Laplace transform we can take with this function, Laplace transform of ft is fs, then Laplace transform of GT we have to find out with the use of second shifting. GT is one special kind of function related with FT. What is G? GT is 0 less than A, GT is greater than A is f of t minus A. So with the help of second shifting we can say Laplace transform of GT is e to the power minus as f of s. F of s is what? Laplace transform of ft function. So what we can say, we find out the Laplace transform of this function and just multiply e to the power minus as. A is what? This value. That is the Laplace transform of GT. So this is the second shifting property for given Laplace transform. And in further we can see the, definitely we can see the example on this. For what this state, if this is our function ft, then if we talk about the GT, GT is same function but replace a value, a. So GT start with a point, ft start with 0. So Laplace transform of this and Laplace transform of this related with e to the power minus as. Clear? Next we go for next property is multiplication by t. Fourth property is multiplication by t. If any Laplace transform multiplied with t, Laplace transform of ft is equal to f of s, then Laplace transform of t ft. See, when t is multiplied with Laplace, then it is given by minus of f dash s. Dash means what? D by ds of s. I can rewrite minus d by ds of f of s. Means we have to find out Laplace transform of this and then we differentiate this with respect to s one time and put one minus sign. So with this, if we find out Laplace transform of t square ft, that is minus 1 to the power 2. This we can standard minus 1 to the power 1 minus 1 to the power 2 f double dash s. Clear? 2 times derivative. So similarly Laplace transform of t to the power n ft is minus 1 to the power n f n dash s. We have to differentiate that function n times. Clear? So for t square 2 times, for t cube 3 times, for t4. What is this property state? If our Laplace transform of e to the power 2t, e to the power 2t is what? 1 upon s minus a is 2. So our fs is this. Now we can say we find out Laplace transform of t square e to the power 2t. So t square e to the power 2t is minus 1 to the power 2t. Then second order derivative d2 by ds square of 1 upon s minus 2. We have to differentiate this function 2 times, then we will get the Laplace transform of this function. Clear? So this is multiplication by t. Next property, fifth one is same, division by t. So for multiplication we have to differentiate, for division we have to integrate our final function by t. So Laplace transform of ft is fs, then Laplace transform of ft, if this function is divided by t, then our is s to infinity fs ds. We have to integrate one time for 1t division. If ft upon t square, So this is s to infinity, fs ds ds. 2 time integrate, limit is s to infinity, not 0. Limit is s to infinity. So for this is the Laplace transform for division by t. Same if we have Laplace transform of e to the power 2t is 1 upon s minus 2. We want to find out Laplace transform of e to the power 2t upon t. Division by t. So what is this? This is s to infinity. Fs is 1 by s minus 2 ds. We have to integrate one time and apply the limit. Integrate one with, this is log of s minus 2, you have to apply the limit, you will get Laplace transform of this. So that is the fifth property of Laplace transform, division by t. Now two important property, Laplace transform of derivatives and Laplace transform of integration, and two more, convolution theorem. One is, and next is the initial value final. So in this lecture I discuss all the properties. In my next video you can see all the examples depend on these properties. So next property is Laplace transform of derivative. Means Laplace transform of, if we know Laplace transform of ft is fs, then Laplace transform of f dash t. F dash means d by dt of ft. One time differentiation is given by s of fs minus f0. If two times Laplace transform of derivative d2 by dt square 2 times, then this is s square of fs minus s f0 minus f dash of 0. Third one, if 3 times this Laplace transform of derivative, this property is very useful when we solve differential equation. So many differential equation with this property we can take Laplace transform, solve it, and at the end again take inverse Laplace, so we will get the required solution. So this is Laplace transform of derivative is very important property for solving the differential equation. If 3 times derivative, then same equation, s cube fs minus s square f0 minus s f dash 0 minus of f0, like that. So this is Laplace transform of derivative. Next if we talk about Laplace transform of integral. Then what this property gives? Very easy Laplace transform. If we have to integrate here, then 0 to Laplace transform of integral 0 to t ft dt. So what is Laplace transform of this is f of s divided by s. So if 2 times integral 0 to, but limit is only 0 to t ft dt is given by f of s by s square. Clear? So Laplace transform of integral, you just find out the Laplace transform of given function. If limit is 0 to 2, you divide with s. If 2 times integrate, then divide with s square. 3 times integrate, divide with s cube, and so on. So this is the Laplace transform of integral. Next is the convolution theorem. Very important property. This is the very good property of Laplace transform. In all integrals we can see convolution. convolution theorem states that if ft and gt are two function where we can give its Laplace transform and it is defined with convolution. What is convolution? Say 0 to t f of u gt minus u du. Both function related with this f of u gt minus u du, then and Laplace of ft is f of s, Laplace of gt is g of s. Clear? Then Laplace transform of ft and gt both multiply is given by, we have to multiply individually of these. Laplace transform of fs and gs. Clear? So this gives with the help of convolution theorem. If two function related with the convolution theorem, then Laplace of their multiplication is just individually you have to take out the Laplace transform and multiply it, you will get the Laplace transform of this function. Next is the initial value theorem and final value theorem. So we can see what is the initial value theorem. Initial value theorem states if Laplace transform of function ft is fs, then if there is limit t tends to 0 of ft, then Laplace limit s tends to infinity of s phi s or f of s. This is the initial value theorem. What means? If Laplace transform of this function is this, we apply the limit t tends to infinity on this Laplace transform, then we apply the limit here also, but what is the solution? S tends to infinity, s f dash s, there t tends to 0. Second is the final value theorem. Final value theorem states if same, then limit last final t tends to infinity of ft is given by limit s tends to 0 s of fs. This is initial value, t tends to 0, and this is the final value, t tends to infinity. So these two are called initial value theorem and final value theorem. Now in my next video you can see all the example based on these property. I can explain you one by one property with the help of examples, so you can better understand how to solve any given function for Laplace transform. That's all for today. Thank you very much.